In 1905, Albert Einstein told the world something that changed physics forever. The speed of light is constant. It never changes. It is the same for every observer, in every direction, under every condition, and nothing in the universe can exceed it. That idea became the foundation of modern physics, woven into every equation, every model, every theory we have built in the century since. And for the most part, it has held up remarkably well. But here is what most people don't know. Einstein himself didn't always believe it. And the way we talk about the speed of light today is missing something important, something that makes the full picture far stranger than the textbook version suggests. Let's start at the beginning. Before Einstein published special relativity in 1905, he spent years working on an earlier theory of gravity. And in that earlier work, he concluded something remarkable, that gravity changes the speed of light. Not by much, but measurably and in a specific direction. Light moving away from a gravitational field slows down. Light falling toward a gravitational field speeds up. Einstein eventually abandoned this idea when he developed the more complete framework of general relativity, and the standard model locked in the constancy of light speed as an absolute rule. But the idea never fully went away. And in 2026, a physicist at the University of Wollongong built a machine specifically designed to test whether Einstein's early instinct was right, whether gravity does, in fact, alter the speed of light as it crosses Earth's surface. His results are controversial. They have not been independently confirmed, and mainstream physicists remain skeptical. But the experiment exists, the data is real, and the question it asks, whether we have been interpreting the constancy of light speed correctly for 100 years, is a question that serious physicists are still taking seriously. Now, here is where it gets even stranger, because in March 2026, something was confirmed in a laboratory that sounds like it should be impossible. Researchers directly measured what are called dark points within light waves, specific points that move faster than light. Not matter, not information, not a signal you could use to communicate anything, but a physical feature of the wave itself, moving at superluminal speed. This had been predicted mathematically for 50 years, and nobody had managed to measure it directly. Now they have. And what it confirms is that our simple picture of light, one speed, one rule always, is not the whole story. Light is more complex than that, and some of what it does exceeds the speed we've been quoting since Einstein. None of this breaks special relativity. The rule that no information can travel faster than light still holds, but it does reveal something important. The way we talk about the speed of light in classrooms, in documentaries, in popular science is a simplification, and like most simplifications, it leaves out the parts that are hardest to explain. There is also the question of what constant actually means. The speed of light being constant means it is the same for all observers, regardless of how fast they are moving. But it does not mean light always travels at the same speed through all mediums. Light slows down dramatically when it passes through glass, through water, through any material. And in certain laboratory conditions, scientists have slowed light to the speed of a bicycle and even stopped it completely. Briefly, experimentally, frozen in place. The photons didn't disappear. They were captured, held, and re-released. The speed of light in a vacuum is constant, but light doesn't only travel through vacuums, and the distinction matters more than most people realize. And then there is the measurement itself. The number we use, 299,792,458 meters per second, is exact. Not approximate, not measured to many decimal places, but literally defined. In 1983, scientists decided that rather than measuring the speed of light against a fixed meter, they would define the meter itself based on the speed of light, which means the speed of light cannot be wrong by definition. We have made it true by construction. And that is a strange thing to sit with, because it means that if light were somehow behaving differently than we thought, we might not even be able to detect it through standard measurement, because our rulers are built from the same assumption.
The speed of light is one of the most tested and confirmed constants in all of physics. But confirmed does not mean fully understood. The more precisely we measure it, the more we find edges and exceptions and complexities that the simple version doesn't capture. Einstein knew this better than anyone. He spent years questioning his own assumptions about light before he got to the theory that made him famous. And the physicists working on this today are doing exactly the same thing. Subscribe, because next time we're covering something that directly connects to this: why time itself slows down the faster you move, and what happens to a clock traveling at the speed of light.